Thank you very much, everybody, for attending this session. I can see a few people still trickling in. I'm Dr. Karimullah. I'm CTO at Pinpoint Medical, a company that's very much in the business of bringing in new technologies to improve healthcare. And what I'm going to be demonstrating a bit, or rather introducing to you today, is one of our concept products that is in development for infection prevention, control, and monitoring. But we do others as well. We look into sort of solutions for cancer diagnostics and things. But today is all about this. And what I'd like to sort of say before I begin is very much that this isn't just about what our product can do or what it is. It's also about getting a discussion going and getting feedback from all of you who would end up sort of being the end user customers or people who could benefit a lot from this kind of technology. So we'd like your positive feedback, your negative feedback, and also your opinions on where else you think this kind of technology can actually help you in your reducing workloads or improving safety. Now, it was really interesting. Just before I get into hospital-acquired infections, and you will know this far better than I do, and Yvonne covered a really important aspect of airborne pathogens, so I hope by this point you believe in all of that. But it's really interesting that a lot of this technology that I started with an engineering background, and she mentioned the lovely Essex boy, Lord Lister, ended up, moved from engineering into the Department of Chemistry in the University of Glasgow, where Lister actually produced a lot of the work for our current infection prevention methodologies. And so it's really nice to sort of see how we've taken all of that nanotechnology that we developed, and in his footsteps, in the same place, we're actually now deploying that technology towards a very similar industry. Now, I don't need to tell you that the NHS is kind of burdened by the issue of health-acquired infections. It's costing a lot, yes. And airborne pathogens are now becoming a lot into the spotlight. They're a major factor, a major player in this issue, right? But it's not just about the patients, right? All these calculations about the treatment, it's about the ward spaces. A lot of it is about the staff, right? The safety of the staff, them having this mental ease that they're in a safe environment, they can do their job, they can focus on it. That's a really important bit of it. And if we consider the WHO report about the pandemic, over 100,000, all the way up to what they estimate, 180,000 staff, healthcare staff, died in the pandemic. And the International Association of Nurses estimate that about 100,000 was because the staff was working at the front line and they got those infections. So it's a really important issue of making a safe space for people to work and for patients to be treated. Now, we know that airborne pathogens are really a major factor in this. But as an engineer, I kind of like to not just look at the statistics, I like to look at dimensions, right? I'm really bad at statistics. So let's look at aerosol particle. Now, when somebody coughs or sneezes, you would generate respiratory droplets. You would generate them while breathing, but you would also generate larger droplets when you sneeze or cough. And some of them are going to fall up to 2 meters. Okay, you can stay away, no problem. But a lot of them are invisible, right? And let's assume the majority of them are from roughly about 5 to 10 micrometers in their diameter. So doing a bit of maths, focusing on that size domain, considering coronavirus, which could be about 50 to 100 nanometers in diameter, you could potentially fit in 1 million coronavirus particles in those droplets, the larger ones. And of course, practically, this isn't necessarily what's going to happen. But let's say even if it was 1/10 of that amount, it's quite a lot. We know that inhaling respiratory viruses actually makes them far more dangerous than just touching a surface or getting them onto your nose. They become a lot more potent. In the case of, for instance, influenza, up to 300 to 30,000 particles is what you need when inhaled to immediately cause a very serious infection. So if we look at the fact what Yvonne earlier said about the sniff and swallow of norovirus, there was even a lot less, right? So things become a lot more dangerous when they go directly into your lungs. And the aerosolization can be because of infected people causing this and spreading it, but also think about when moisture moves through ventilation systems, it can collect stuff, it can move that around. And so this is a major issue from multiple aspects. It can pick up things, it can carry things as well. So yes, we can put patients with masks on, they might not be the only source for this sort of airborne transmission. A really important thing to know is that these kind of droplets don't necessarily just fall 2 meters away. They will travel miles. And they don't just hang around for minutes in the air. They can stay up to days depending on the climate. So depending on different locations and countries, it will vary. So they're really, really a potent way of transmitting disease. Now, it's not just a hospital problem, right? This is a social issue. Because think about the spaces where ventilation is a lot less transport, airplanes, right? How often, I was just traveling on the plane recently, and I remember my wife was kind of a bit freaked out at some point because there were a bunch of people coughing very close by, and she was like, oh no, another trip, I'm gonna get home, I'm gonna be ill again, or this holiday is gonna be wasted because of this. And that's a continuing thing. Now, whether airlines want to necessarily know, airports want to know what's there, probably not. Nobody wants to park an airplane with 300 or more people inside and have to quarantine them. However, what we can potentially do is implement technology that can immediately sort of nip this in the bud as much as possible. And that can be done through improving our disinfection methodologies. So while we can, in public spaces, do more ventilation and all, we have to realize that's not always the case in every environment. And thinking about schools, going back to something my boss said a while back when I was still lecturing, and he's a lovely guy, so please don't judge him for this, but he used to sort of say this to me, Affar, students are like rats. They could bring the plague, and we still have to deal with it at the university. And it's nothing against students, they're just doing what they do, but it's very much a problem when we're working and how we deal with these issues. So our aim as a company, and we noticed this issue before the pandemic in 2018, which is when we founded it, and this was one of our first sort of concepts that we took forward, was to improve air quality and also detect things so we can monitor what's in our air. And while there's a lot of technology right now, cleaning surfaces, fantastic technology upstairs and also internationally, which is decontaminating air, there's still quite a bit of issue when it comes to repeatability of those techniques. So we still have a long way to go in terms of what we do with technology, how we improve it to actually make this a lot more effective. But one thing we really recognized early was there's still a big problem when it comes to testing air. You could sample in a hospital, you could sample the corner of the room, it then goes for a test, 2 days, 3 days. By that point, this conference is over, right? And not only that, taking something from what Yvonne said, evidence-based approach. If we know something on the immediate, we can also help that evidence-based approach. You could have monitors in the toilets, you could have monitors in the wards, in the hallways, collecting this information so we can actually improve our protocols, improve our standards in how we do things. And that's what we're trying to do. So what we want to achieve is a system that can actually not just decontaminate air really well, but also detect multiple pathogens and inform us better of what's in our environment so we can actually take preemptive measures rather than reactive measures. So I'd introduce you to our concept, the IAQ, an intelligent air quality system, which utilizes photocatalytic filters for the decontamination process. And we combine it with some unique new technology that dampens vibrations in air to reduce sound. So we want to try and push the standards in terms of the quality of our product. And we combine it with our disposable plasmonic assays. These are biosensors, like a cartridge-based system. They can detect multiple diseases in a single test, and you can have multiple tests in a single cartridge. And at the end of the day, they're disposable. You just chuck it away once it's done, or send it back to us for recycling. And you put in another cartridge to do the test for the next week or days, or however many tests you wish to do. We'll start with the first bit of technology. So there are two really important technologies that make this whole thing. And the first is our ceramic filters. I've got a few here, and we've got our booth upstairs right at the entrance, so if anybody would like to look at them or find out more about them, please do visit us. And these ceramic filters are very porous. So we're not trying to capture things and create another problem when you're trying to change those filters. You could potentially expose them, bring them back into the environment. We want to destroy them right there and then not have to worry about it in the future. So these use a photocatalytic coating. And under UV conditions, they allow a lot of air to flow through. With the UV, we're decontaminating whatever's passing through the air. So it's like a chemical reaction without requiring chemicals, essentially. The chemicals are all on the surface, and the energy provided is all from the light. With the porosity, you can actually pass more air, and that means you can actually clean out a larger environment much faster. It also removes hazardous gases, so there are additional benefits to the overall process, and there's no ozone generated from these. And another thing to really cover about this is the fact that when bringing this kind of technology into the market, into application, we have to be sort of consider the financial aspects. You don't want a technology that is really capital heavy or problematic for the industry to actually take into account. So these kind of filters, we can design them in different ways. We can design them in different, or produce them in actually different dimensions, but they could fit into ventilation systems, or they could be standalone, and they could fit into old hospitals or new. So we reduce the kind of cost of actually implementing this kind of technology. So coming to the disposable plasmonic assays. Now, this kind of started a long time ago. It's research that was done over 10 years by myself. And this is based on some nanotechnology. You can kind of see these little shuriken-shaped structures. Those are actually nanostructures, 500 nanometers wide. You can actually see blue spots there. I hope the slides probably should have made it a bit bigger. But the blue dots there are actually coronavirus particles, actually from a test. And this photonic nanostructure actually allows us to produce a biosensor. And the way we manufacture it is the same way we do Blu-ray manufacturing. So it's really cheap, and that's why it's disposable. And with a bit of chemistry, nothing massively new. We're taking the concept that exists in the lab, and we're just putting it on our sensor, and we're trying to automate the overall process. So we're not completely putting man on the moon kind of scenario here, but we're taking what actually exists, making it more practical, and trying to reduce the burden on staff at the kind of work they have to do, yet provide a lot more capability in collecting information and knowing our environment a lot better. In our paper in 2023, we actually showed we could detect Zika virus and norovirus from a single sample in a single experiment. And we also detected coronavirus. We couldn't include all of them. There's a contamination issue. There's problems in terms of where we do coronavirus research. Perhaps it's reduced now, but back in the day, it was a difficult thing to touch in the university, at least. That's just a little show of the kind of prototype at the moment that we have of this biosensor, which is functioning in our labs. And as a company where we're developing this, we're going to make a much more compact unit that fits in the overall product. And so our aim is to kind of create this system where everything is there in one. So reduce workloads, improve disinfection, provide information that is difficult to capture on a real-time basis at the moment, and also reduce noise so it's not something that is causing problems to patients or making more difficulty for people implementing this kind of technology. And we want to push the boundaries of the standards that are there. The standards are like, it's an evolutionary process. They're limited by the kind of technologies that's there. We want to provide that new technology and push the boundaries of those standards as well. And so with that, I'd like to thank you. But again, this is about getting feedback. So I'd really like to know a lot more from you guys. What do you think about this? Would you like technology like this? Where do you see, apart from where we are implementing it, where else would you like to actually see it implemented, and how can it help you? We're upstairs just at the entrance, so if anybody would like to look at the filters And also, what I forgot to show in my talk here, the biosensor cartridge. This is just a little prototype to demonstrate what kind of size and dimensions they'll be. Then please feel free to do so. Thank you.